Today we're talking about kind of a confusing set of topics here. We've got some single events, and we're looking at overlapping outcomes of single events, and then we're looking at also dependent or independent situations for multiple events. So I want to keep contrast between whether we're talking about a single event or multiple events happening. And I don't know why these are taught together because it's just confusing. But that's how this section is. So let's talk about overlapping outcomes of a single event. Now, what we need to first discuss is whether the outcomes are mutually exclusive or not mutually exclusive. Mutually exclusive is when two events can't happen at the same time. Excuse me, two outcomes can't happen at the same time. This is another thing about this particular subject is they often call it mutually exclusive events, but it should really be called mutually exclusive outcomes. Say you flip a coin. When you flip a coin, the event is flipping the coin, but the outcomes are heads or tails. You can't get both heads and tails. You get heads or tails, so we call that mutually exclusive. They both can't happen at the same time. So here's another mutually exclusive event. Probability of getting a queen or a king when you draw from a deck of cards. You're going to get a queen or a king. You can't get both at the same time. So it's 4 out of 52 for the queen and 4 out of 52 for the king. So it's 8 out of 52 for getting either one of those. Now, not mutually exclusive is when you try to get a queen or a club. The reason is there's 4 queens and there's 13 clubs. So you'd think it's 17 out of 52, but actually you counted one of those cards twice, the queen of clubs. You counted it when you counted the queens, and you counted it when you counted the clubs. So you need to subtract that one card since you counted it twice. So it ends up to be 4 out of 13. There's some overlap in the outcomes of queen and clubs that you don't see with queens or kings. So here's another situation where we see overlapping outcomes. So let's say I want to find the probability of getting an even number or a number less than 5. So I'll just go through and circle all the even numbers red. So that's going to be 4 out of 8. And now the numbers less than 5, I'll circle blue. That does not include 5. So that's also 4 out of 8. So it looks like it's going to be 6 out of 8 because 5 and 7 don't qualify. But when I do the problem separately, I look at the probability of getting an even number, that's 4 out of 8. I look at the probability of getting a number less than 5, that's 4 out of 8. That adds up to 8 out of 8. But I know it's not 8 out of 8. The reason is we counted two numbers twice. We counted the 2 twice and the 4 twice because they were both even and less than 5. So you need to subtract 2 out of 8 to end up with 6 out of 8, which we know the answer to be. So this is the general formula for adding two outcomes that are not mutually exclusive. There's overlap between them, and this is the overlap, what A has in common with B. So let's try a similar problem. What's the probability of getting a face card or a heart? So this is just one event. You're drawing a card one time. You're trying to get a face card or a heart. What you need to ask yourself, are these outcomes mutually exclusive? Can a face card be a heart? And of course the answer is yes. So we're going to write the formula down. The probability of A or B occurring is the probability of A plus the probability of B minus the overlap. So let's see, how many face cards are there? There's 12. There's Jack, Queen, King for all 4 suits, so 12 out of 52. What's the probability of getting a heart? Well, that's there's 13 hearts in the deck. That's 13 out of 52. Now, how many of those face cards are hearts? Well, there's the Jack of Hearts, the Queen of Hearts, and the King of Hearts. So there's 3 cards that are both face cards and hearts. That means there's 3 cards we counted twice. We need to subtract out 3 so that we end up only counting them once. And so that gives us 11 out of 26. Okay, so now we're looking at probability of multiple things occurring. There's 2 types. There's independent events and there's dependent events. In an independent event, the first event does not affect the outcomes of later events. So some people perceive, though, that, if I got 10 heads in a row when flipping a coin, the next one's really likely to be tails because I got 10 heads in a row. No, it's still 50%. No matter how many heads in a row you get, the next one is still going to be 50% of getting heads or tails. This is a game called roulette. There's 38 numbers here on this wheel, 1 through 36, and then a 0 and double 0, which are green. And Vegas will pay you 35 to 1, which means if you bet $1, you will win $35 if you put $1 on any one of these numbers. So they're making money because odds are 1 in 38, 1 out of 38, but they're only paying you 35. Now, funny thing, when they put this tote board up, I think it was around 1995, they started putting these tote boards up. People started betting much more on roulette because they thought, oh, there's been 7 reds in a row. The next one's going to be black. But that just isn't the case. So there is this perceived idea out there that just because you've got so many reds in a row, the next one's going to be black. It just isn't true. I mean, the probability doesn't change because the first event or the first 10 events has no effect on the next event when the events are independent. By the way, I did some research on this tote board because I realized that the probability of someone getting 7 19s in a row is so astronomical. I mean, if you bet $1 right here on this first 19, you would have won $35. And if you let it ride, you would have won 35 times 35 for the next 19, and then times 35 again. If you would have let this ride 7 times, you would have won $1 billion. I mean, that's ridiculous. Turns out they were just testing the machine. That didn't really happen. Yeah, someone was just walking by and took a picture of that. It's pretty funny. All right, anyway, dependent events is when the first event does affect the outcomes of later events. Let's say you're trying to draw 4 aces from a deck of cards. Well, the first ace is going to be a lot easier than drawing out the second, third, or fourth ace. The reason is, with the first ace, you have 4 aces that are in the deck. So your first ace will be 4 out of 52. But with the second ace, there's 1 less ace in there now. So now it's 3 out of 51. And then the third ace is even harder because there's only 2 left. So it'll be 2 out of 50. And then the last ace, there's only 1 left, and that'll be 1 out of 49. So it becomes increasingly more difficult to get those later aces. So let's look at some independent events here. Here I have a bag. It consists of 3 red marbles, 4 white, and 2 blue. I want to know what's the probability of getting red, comma, another red. So this is 2 events right here. You separate your events with a comma. So the probability of getting the first red is going to be what? 3 out of 9. Now, you're putting that red back in the bag. So now there's still 3 red marbles in there when you go to take out the second one. So this could be reduced to 1/3 times 1/3, which is 1/9. Now let's look at the probability of getting white, then blue, then blue. And remember, we're putting the marbles back in the bag. So that'd be 4 out of 9 for the white. Blue would be 2 out of 9. We put the blue one back in, and it's still 2 out of 9 for the second blue. So this works out to 16 over 729. So we just saw independent events are when you replace the marble. Now, if you don't replace the marble, then you find yourself in a dependent situation. Now, same problems, but now we're not replacing the marble. So probability of getting red the first time is 3 out of 9. Now, that means there's 1 less red marble in the bag. So now the probability of getting red again is only 2 out of 8. 2 because there's only 2 red marbles, and 8 because there's 1 less marble in the bag. So that reduces to 1/3 times a fourth, which is 1/12. If we do, we put all the marbles back in, we do problem 2, white, blue, blue. So white would be 4 out of 9. And then we take a white one out. Now there's only 8 marbles in the bag, so getting a blue one would be 2 out of 8. And we take out a blue one. Now there's only 7 marbles in the bag and 1 less blue, so now it's 1 out of 7. And that reduces down to 1 out of 63. And we're done for the day. All right, have a good one. See you next time.